Hey guys, it is John here. In this video, my goal is to cover everything you need to know for the SAT involving Desmos. Every single minor technique, every single rule, all the math that goes along with it, all of it is going to be covered in this video. Because the truth is, Desmos is still the ultimate SAT cheat code. When you take the SAT, you are given the ability to use a full graphing calculator for literally every single problem in the math section. And the truth is, this is usable for, at minimum, about 50% of the problems, and even more if you include all the different times you can just use Desmos for minor parts of different problems. It's unbelievably powerful, and even though you might have heard some people tell you that Desmos is becoming less useful, the truth is, Desmos is literally just a graphing calculator. It does math. Desmos is just a math tool. In order for Desmos to not become usable anymore, they would literally have to take all of math off the SAT. As long as there is math on the SAT, Desmos will be usable. Yes, there could sometimes be problems that cannot involve Desmos at all, but the vast majority of problems can use Desmos because that's what math is. And you might be wondering, how is this video going to be different from all of the other SAT Desmos videos you've seen online before? Because trust me, there have been many, because a lot of SAT YouTubers want to focus on Desmos since it's a really easy thing to talk about. But the truth is, the thing that makes this video different is that I'm going to try to break down Desmos rules, not just by saying the rules, but saying why they specifically work. For example, instead of just telling you how to do a single variable equations problem, or how to do a systems of equations problem, or how to do regression, my goal in this video is to actually try to break down for you why that works and how the math is actually playing with what you're using Desmos for. This is so valuable because you can kind of think of it a little bit like a chef in a kitchen. Let's say you have a chef who just memorizes a list, this is supposed to be a chef's hat by the way, who just memorizes a list of different things in a cookbook. So they learn recipe 1, recipe 2, recipe 3, recipe 4. They could probably make those recipes really well, but if somebody goes up and asks them, hey, can you make some kind of other recipe that's not one of these 4? This chef would just be completely cooked. They would have, no pun intended, they would have no chance of being able to figure out this other recipe because the chef is only good with these 4 different things. The goal instead should be to figure out how food works. How do you even make good food in the first place? What kind of spices do you need to put in food to make it taste good? What kind of elements of food are key to make a really good dish? If a chef knows that, no matter what people ask them to make, the chef is still probably going to do a really good job because they just know how food works. And this is kind of like with Desmos as well, because if you just know a list of different rules, if you see a math problem that just violates any of those rules, even in the slightest, you'll have no idea what to do. But if you know why it works, it'll still make sense to you, even if there are some small variations like what you'll see on the SAT. Also in this video, we are covering a lot of material. The goal with this is to really make it a fully comprehensive guide of Desmos. So you can see all of these represents a different practice problem we're going to be talking about in this video. So there's like over 50 at least I'm going to be going over. So this video is going to be long, but the goal with it is really to make it so if you watch this video, there is no chance of you not understanding Desmos by the end of it. I've had students tell me before that they've watched a lot of Desmos videos, but they still just don't understand certain parts of it. The goal is to make it so if you watch this video, it would basically be impossible for you to still be confused on all these different Desmos things because you're just going to have such a good amount of knowledge on it. But I can obviously still answer any kind of questions you guys ask in the comment section. So if you have any thoughts at all, feel free to ask that. If you want to know why you can personally trust me, I've scored a 790 in the SAT math section, so close to 800. Really unfortunate about that. Maybe I'll try to fix that soon. I currently own the largest SAT community on this website called Skool.com, called Gamify SAT. And my goal is to make the channel that you're watching right now the best SAT YouTube channel on YouTube as well. Okay, let's get into Desmos and just start with the basics first of all. This is what you see when you open up Desmos for the very first time. It's important that you try using the College Board version of Desmos because there are some small, minute differences between this and the regular version. Not enough to make it matter too much, but it is just valuable to use this. And you'll notice it is because it has a green thing at the top. The regular Desmos is black at the top. And what Desmos even is just a graphing calculator. So obviously you can do calculations. You can do 1 plus 1 and here you get 2. But also you can do stuff with the graph here. If I was to type something like X, we can see here, now there is a line on the graph that we can do stuff with. And so a lot of the more complex stuff with Desmos involves the fact that you can use graphs, not just these calculations over here. But if you do want to do some calculations, here's a few things you should know about Desmos first of all. First, there are a bunch of different so-called functions that you can use in Desmos. I say quotation marks because I'm going to have a different definition of functions later in this video, but these are the Desmos functions. So you can, for example, can say mean of 1, 2, 3, 4, 5, or whatever numbers you want. And you can just see this would be the mean of these numbers. You could also do the same thing and say the median of those numbers. We could find the sine of a random number like 1. We could do the cosine of it or the tangent of it in the same exact way. If you want to know what percentage of a number something is, you could say it's like 6, 7% of 67. I got this percent of thing just by typing the percent symbol on my keyboard. If I want to find the minimum of a group of data points, I can say minimum and then just list a bunch of numbers, and it shows me, yeah, 1 would be the smallest one there. That's the smallest or minimum value. Max works the same way, it just gives you the biggest value of everything you see. You can also do total, which is basically just the sum of everything if you add it all together and, make the sum of it basically. You can do SQRT to make the square root symbol in Desmos and do the square root of whatever you want. You can do CBRT to make the cube root and do the cube root of whatever you want. And if you want just a random root that you can decide for yourself, you can say nth root by typing all of that. And now you can put whatever root you want, so like 6 root, and I can choose whatever number I want there as well. Two other useful functions are the midpoint and the distance function. So if I was to say here, a is equal to some point, so like let's say 5, 6, and this is just also works as a constant, by the way, there's no difference just because it's capitalized. And then if I say b is equal to another thing, like say 1, 2, I can now find the distance between these 2 points in space using this thing distance. I can just say distance a, b, and we get that 5.66 basically would be the distance between these 2 dots. If I did not put them in this format, I could also just do it manually by just saying here like 1, 2, but keep in mind they must be in parentheses. That's a big thing a lot of people mess up the first time. They forget to put it in parentheses. So it has to be either in this format or in parentheses. Likewise, I can do the midpoint. What this just shows is what the point in between 2 things would be. For example, this red dot between this black one and the purple one would be 3, 4. So the exact center would be that. Here are a couple of slightly more complex things you can do, but this is still honestly pretty simple. If you type X or if you type Y, it is going to perceive that as a variable. What a variable is basically one letter that can represent every single number in all of existence. So when I type X or Y here, what I really am typing is every single number ever made, just this is a smaller way of writing it there. However, let's say I want a letter to represent just one number rather than every single one. I can do that by just typing some random letter, like I could say A, and then say equal to whatever number I want. So I can say A is equal to 4. And when I do this, I also get this slider here, so I can literally move it around to see what numbers I can do. I can make it bigger, so I can have 100 as being the biggest possible number by doing that. I could have negative 100 by doing that, or just whatever ones I want. If I want to change the step, aka the amount that increases with every single move of my mouse, I can say that there. And now it only increases by 5 rather than increasing by every single number imaginable like it was before. So this will be important later on. You'll see why these are important. Another letter you should be familiar with is this one E. Many people get confused on this. This is a special thing in mathematics and physics that is just a meaning of the letter E. So if you type E, what you're really getting is this exact number. It is not usable as a constant or a variable in the ways I just described there. Likewise, you can type points in Desmos and have those points appear on the graph. So I could say here 4, 5. Now we have a point on the graph that is 4 moving horizontally and 5 if we go from down to top. So that'd be that there. I can do the thing with called a table where I can basically add multiple points at once. So I could say 1, 2, and then 3, 4. So now we have multiple different points. It's kind of just like a combination thing here that you can use. You can also make what is known as a list. So if I type like a random, let's say constant, like let's say A, and then say equal to square brackets, now everything that I put in this list separated by commas will be part of A. So I can say 5, 6, 7, 8. Now those are all contained within A. And I can now also do special things with this. For example, I could say mean of A, and that would give me 6.5 because the mean of these numbers would be 6.5. I could also say median of A, and that gives me 6.5 as well because that would also be the median of it. Also, if you go over here to the wrench, you can switch between radians mode and degrees mode. This is really important, especially for sine, cosine, and tangent problems that we'll discuss later on in this video. So be sure to do this whenever you're using Desmos. It is going to start in radians mode every single time, so you should be warned that if you do something with sine, cosine, or tangent, it's going to be messed up if you don't switch it to degrees mode as the first thing you do. And then, of course, you can just do whatever random calculations you so want. I could say 1 plus 1, get whatever number for that, minus 6, multiplied by 7. A bunch of great stuff like that. You can just type it using this. I would recommend to only ever try to type stuff in Desmos unless you really need to click on something, like if you need to click on this for radians or degrees. Everything you really need to do can be just done through typing. For example, if I do 56, I can click the / thing on my keyboard to get a divide thing and divide it by some number. If I want to do the exponent, I can just do shift and then the 6 button on my keyboard, and that gives me exponent, which I can make whatever I want. If I want to do something to a group of numbers, so if I say 6 plus 7 and I want to do something to both of these combined, I can highlight it and then just do whatever I want to do, which is usually going to be dividing it by some random number, like I could say 8. Okay, now all the basics are out of the way. Let me go ahead and actually do a few things here just to show you how this stuff can work. So this one here, it says the list gives the number of hours of 9 students spent studying for an exam. What is the difference between the mean and the median of the 9 values? So like I just showed before, I can just say A and then put a list there. So I can do in this list 4, 7, 8, 9, 12, 13, 15, 20, and then 38. And then I can go ahead and do the mean of A and then subtract the median of A, which will just give me 2 for the answer here. So 2 is that. This one here, it says we have point A with these coordinates and point B with these coordinates. M is the midpoint. What is the distance from M to the origin? Origin is just another way of saying the 0, 0 point. So basically right here, this purple dots. So I can just go ahead and write these points. I can say A is equal to -5, -2, and then I can say B is equal to 11, 10. And then I can find the midpoint of that, saying midpoint of A, B. And then I can just see what is the distance between this 3, 4 points. So distance, and then let's say 3, 4. And then the origin would just be 0, 0. That'd be 5. So therefore the answer to this one would be A5. Keep in mind, this is definitely like the least intuitive part of this video. Everything else in this video is going to have a very logical, clear reason behind it. But if you don't know how Desmos works, none of that even matters in the first place. So I really would recommend you to just spend a bit of time understanding this different stuff, understand how Desmos works to use, how it feels to play around with different stuff. And you can probably, understand this a lot better than if you're going into this completely blindly. So spend some time, try to understand how this works before you move on, but that is the basics there. Okay, now the first thing here I really want to show you is this thing called a single variable equation. Now you may think this is really basic, but it does really help to understand the logic behind why this works the way it does. So for most of math, what you can just literally do is type something plus something minus something, multiply by something, divide something, and just get an answer out for that. So 3 plus 3 is equal to 6. Pretty simple. We just do something to 3 and then we get 6 out on the other side. But what if you wanted to go backwards? What if you know that it is equal to 6 and that you have 3 at the beginning, but you do not know what is in between these two things? Well, in that case, you can write 3 plus, let's just say, x is equal to 6. So this is really like working backwards. It's like if you look at somebody who's like really successful, like if you look like a billionaire, and you asked a billionaire, how did you get all the money that you have now? The billionaire would probably be like, okay, first I did this, then I did this, then I did this, then I did this. And that's like these steps that billionaire went through in order to get to this point. Now, we just see the final results, but we don't see those individual small things that happened. And that's kind of like what we're solving for here. We're solving for this unknown value. Now, one thing that you may be thinking about here when you see this, I use this letter X for the thing here. And you may remember that I just said in Desmos that X and Y are the two things that are variables, meaning they're equal to literally every single number. When you're dealing with a single variable equation, that doesn't matter. You can just pretend like X is just one number and it's okay. You don't have to worry about anything else. So just don't worry about that. Don't get confused. This is just really as simple as it looks. And so to solve it in Desmos, all I need to do is just type in this exact thing. There's not much more to it. I can just say 3 plus X is equal to 6. We see here that it just passes through exactly at this 3 thing, and therefore that is why 3 would be the answer according to Desmos. If you're wondering why there's this line here, that actually has a very logical reason behind it. It's because Desmos is still treating X like all real numbers. Desmos did not get the memo that this is just supposed to be only one number. So it's still trying to pretend like X is literally equal to everything. But it's encountering an issue here because it's trying to make X something other than 3, but it's just not working. If they make X equal to like 5, then we get 3 plus 5, and that does not equal 6. That doesn't work there. If they try to make X equal to like -7, 3 plus -7 equals -4, not 6. So they're kind of like confined to this one part where it's equal to 3, and that's why literally every single place they try, it must equal 3. So that's the reason why they're going through exactly 3. So 3 here would be the solution. Let's go through some practice problems. How many distinct real solutions does the equation below have? So for that problem I just showed you with the 3 and the 6, there was only one solution because it had only one line that passed through it. But there theoretically could be multiple different solutions. So I could say here 3x minus 12, and then say that's equal to x plus 4. We see here now they have 2 different lines. So both of these would work as solutions, so therefore the answer would be C, exactly 2. This one, what is the nearest positive solution to the given equation? So I can just type here 7x squared minus 3 is equal to 41. And we see for this here, they're saying the positive solution, this one would be negative. So therefore the answer is this 2.507 number, and it says nearest thousandth. So I can just write here 2.507. This one, what is the solution to the given equation? I can just go ahead and type that. We get this here. But you'll notice here that it's not giving us as simple of an answer. If we have to really like scroll in here, and even then we can't be entirely sure what the thing is, because like it could theoretically be like 8.001. It might just not be showing it because it doesn't give us an exact intersection. When there are any confusion or difficulties with doing this method, you can just separate each different side of the equation into its own y equals thing, and that'll show you the right answer. What do I mean by that? I can just say y is equal to the left side of the equation, and then also y is equal to the right side, which would just be 7. And then it gives us these things here. It gives us two different squiggly lines, or I guess one squiggly and one is just a horizontal line. And we can just see here where they intersect. We can get rid of this blue thing by clicking that. So we can see here 8, 7. So that is where we're getting this 8 from, so it would be 8 for the answer. We know it's not the 7 here because it's asking for x in this thing. X is always the value on the left of the thing. So the first one is X, second one is Y. I'm going to get into more what this means when I say these two different things and why they're squiggly, why we're looking at this thing in a second. But for right now, you just need to know if it's confusing, if it doesn't work for some reason as a single variable equation, you can go ahead and do this. Let's bring in some more factors here. So this says here in the given equation, K is a positive constant, which gives all solutions for X in terms of K. So again, I would start here by writing out this thing, x squared divided by 4 minus 5k is equal to 0. But we'll notice here we have k. That is a constant because that's not x or y. So that is equal to literally just one value, and we're trying to see what x would have to equal in terms of that. So you may be kind of confused what we're doing here. Why is it giving us this information? But here's the thing you should know. Whenever you see a math problem with a letter in the choices, you can just choose whatever letter you want and just see if it works. So what that means for this one here, I could just say k is equal to, and I could just say 8. That's just a random thing off the top of my head, just a random number. I just says k is equal to 8. That's just the first thing I thought of. And so then I can go ahead and plug in each of these different answer choices and see if that works based off this thing that I was given. This one says plus or minus square root of 5k. So I can just say square root of 5k, and that would give me this 6.32 number. Does x equal that? If I look here, no, x equals this like 12.649 number. So that cannot be the answer. B, plus or minus 2 times that thing. So I can say 2, and then that gives us the 12.6. Oh yeah, so the exact same number as shown here. So therefore B must be the right answer for this. If you don't believe me that it can be literally any number, just watch. I can go ahead and move this thing around. If I make k equal to like, let's say 10, now this is 14.14 and this also is 14.14. If I even make k equal to like 6, 7, we can see here this would be equal to 36.60 and this would also be 36.60. We have another line here because they said plus or minus, so that's the only reason we have another line. But it's going to be the exact same thing as the other one here, just negative. So at this point, I'm really kind of pushing into the next topic here, but I'll just go ahead and explain this anyways. For all of the stuff we've seen before, they had at least one solution. Like every single time you saw a line here, that means there's at least one solution. Many times we saw 2 solutions so far. But this here says that there are no real solutions. So for that to be the case, it will literally have to be the case that there is no line being shown at all at that place. So I could type here x squared plus 12x plus c is equal to 0. And then just say c is equal to whatever. So we're trying to make c equal something where there's now no line being shown. So I think none of the ones I'm given work, so I'll extend this. So yeah, if c is equal to 37, yeah, there's no line there, so therefore there would be no solution. But whenever you're dealing with no solution, or if it says infinite solutions, I would always suggest just immediately going into the y equals thing, because there's a lot of ambiguity that can go on here, and no solution and infinite solution usually looks the exact same. So if I do this thing with y and have both of those, we can now see here a more clear demonstration. And so what we're trying to do here, again, this pushes into the next topic, but I'm trying to make it where there's no intersection between the blue thing here and the purple thing. So if I make c literally equal to, yeah, it was the 37 before. Yeah, it was equal to 37, I think, before. So yeah, there is the one place where there's no intersection between that and this. If I made it even just one lower, now there is at least one intersection. So there would be one real solution. So for no real solutions, we have to make it at 37 or higher. It says, what is the least integer value of c? So the least one would be 37. You can't go any lower than that or else it breaks. By the way, integers mean whole numbers, so that's why I just did 36 and 37. Okay, so for this here, this is also a single variable equations problem. Though we have p here instead of x, it works the exact same way. The one way I would suggest to solve it is just put x there instead of p. The reason why I recommend putting x instead of p is just because it works a little bit simpler. Otherwise, you're gonna have to deal with constants and sliders, which is just a lot more confusing. So I just do it like this, equals 5 divided by x plus 3. Okay, we see here -4. Okay, it doesn't work exactly, so let me go ahead and put it y again. So y equals that, y is 5 divided by x plus 3. You can see here when I do that, we now have, multiple different intersections. This is like a weird thing here. It says here p must be greater than 0, so that means we just choose the positive one, so we just ignore all the stuff over here that's negative. If I go over here, it's kind of hard to see, but yeah, there will be an intersection when p is equal to 27. Therefore, the answer to this problem must be 27. Let's move now into the systems of equations. Every single thing in life always has an input and an output. And that's not meant to be some kind of like philosophical, metaphysical thing here. It just is the truth. Everything has an input and an output. Think about the video that you're watching right now. I had to put an input in, the hours it took to plan this video, to make this video, to get the problems for it, all that stuff. And now the output from it is that you're going to watch this video and probably actually improve, understand Desmos better than you did right now. The input is the time I put in. The output is your understanding, improving about Desmos. Think about other things in life as well. Like think about your time studying for the SAT. Maybe you spend 3 hours studying for the SAT, which obviously is not a lot of time. This video probably alone might take more than that. And so as a result, you might, get like 1,000, not really the highest score. But maybe if you spend more like, 30 hours, you might be able to improve your score to more like a 1,200. If you spend like, let's say 100 hours, you might be more in the range of getting like a 1,400 plus 1,500. So that is how it works. You have an input, something you do, and you get an output, which is the result. And the reason why I care about this so much is because you can show this very well with math. Think about this. If you have a table here and an x value and a y value, what this is really showing is x is the input, y is the output. So if you've ever seen a table in math, this is what it really means. And so you put, random numbers in for x. Let's say this is the amount of time studying again. 3 would be equal to a 1,000. 20 is equal to a 1,200. So the input is the hours, the output is the SAT score. And then 100, let's say that's equal to a 1,450. And so honestly, this is really great. This is a great way of showing how math works, how inputs work, how outputs work. But what if there is an easy way we could show this? The easier way is what is known as a function. Notice this is different from the Desmos functions I was talking about before. Those were just different Desmos techniques. This is actually what math is built on. It's called a function. What a function looks like is something like y is equal to, this is just an example, it's not necessarily related to that, 3x plus 7. Think about it, this would also work as a function because you have this equation here where you can put in different values for x and get different values out for y. If I was to put in the value 0 for x, you could do 0 times 3 plus 7, so 7 for y. If I put the value in 1 for x, you get 1 times 3 plus 7, and that gives us 10. If you put the value 2 in, you would get here something like, 13. You see here, I'm putting in different values for x, and I'm getting stuff out on the other side. And so there are plenty of different ways I can write this kind of function. I can write it like this. I could say y is equal to, 3x squared plus 7. I could say y is equal to just like 3 plus x. I can say literally whatever I want. It just depends what kind of function I want to make. But then here's where it gets really important for the SAT. You will often see times where there are 2 different ones of this. So there might be one function and then another function. Let's even just pick these 2. And then when you put those both on a graph, you're going to see 2 different lines. Like for this one, I'm probably going to see a line that looks something like, this, and probably a line for this one that looks something like, let's just say this. I don't know if that's exactly what it looks like, but that's just my guess. You'll notice here that they intersect at different points. What these intersections are known as solutions. So this would be a solution, and then also this would be a solution over here. And what this really means is like that's the matching up point. That's the place where if you put in the exact same value for these, you get the exact same value out. It's kind of like if you and a friend both study 3 hours for the SAT and you both end up getting a 1,200 as a result of that on the test, both you and that friend both, this would basically be a solution. You both did the exact same thing and you got the exact same thing out. And usually that's not going to happen. For most of these places, there is a completely different value for this one as there is that one. So when there is an intersection, that's a really, really big deal. And so that's why they're known as solutions. If this is the first time you've ever really thought about math in this way, this might really be blowing your mind, honestly, because this is a much more logical way to think about it than just like, oh, you're making a system of equations, you just find the intersection. Like this is actually the reason why it works. And so you can probably guess what I'm about to say next. You can also have situations where there are no solutions. If you have one line that goes like this, another line that just goes like this, they never touch each other at a single place. There would literally be no solutions for these two lines. Likewise, if you have two lines that basically match up each other perfectly, you would say they have infinite solutions. Literally every single point along these, it's not perfect here because I kind of messed it up down here, but in actuality, it would be the case literally every single point touches each other exactly. They're the exact same line. So now I'm going to go ahead and show you some examples of how that might actually work in Desmos. So we have these two equations. So equation, just another way of saying a function, and saying what is the value of x plus y. So first thing I would do, I just type in each one of these, and then we get here this exact thing, 3 and 5. And so x here would be 3, and then y here would be 5, as shown by this intersection. And so we just do 3 plus 5, that of course is equal to 8, so therefore 8 would be the answer here. I know there's a lot of setup for this, but in actuality, these problems are very, very easy to solve. Okay, this one here, I'm just gonna do the exact same thing yet again. We got these two different things. One is really curved, one is straight. It says, what is the greater of the two y coordinates? So the two y coordinates we'd be having would be 6 and then 2, so of course the bigger one would be 6. This is gonna get a little bit harder, but it says this one here, system D and E are both constants. If it has infinitely many solutions, what is the value of D plus E? First thing I should point out to you is the fact that E, like I said before, if I just type in E, that's going to give me this random number. So I have to actually replace that for a different one because otherwise it is not going to work. It's just going to pretend like it's equal to that number. So I just chose F instead. I'm not really that creative. And so I'm going to choose here, make both F and D a slider. So now we have D and F. And so what we're trying to do now is we're trying to make it where both of these lines have infinite solutions, aka they're literally the exact same line because they touch at every single place imaginable. So I'm just going to go ahead and move it. No, this isn't really the most scientific way of doing this, but I can just, kind of see where it works. So, if I move this, if I move F around, if I make that a bit bigger, where would I have to put it to make these the exact same line? And it might just be, yeah, it looks like it's just exactly there. If D is equal to 8 and F is equal to 28, if I go all the way down here, if I make this go away, they're the exact same line. And so it's asking here, what's D plus E? So D plus F would be 36. So you're seeing here, you can literally kind of like cook the books in a way to make it so they have no solution or they have infinite solutions or whatever, just depending on where you make these. Remember how I told you the sliders are important? This is why they're so important, because you sometimes don't even know where to make the sliders until you see what the graph is showing. Real quick, I could also make it have no solutions. If I make F a number like this, a number like -10, now you see they don't touch each other a single place anywhere along the line. So now they have literally no solutions, no things at all. Remember this problem over here, this is why it worked. What I literally did there was I made both of them into an equation, into a function, and I just found where would I have to make C go to make it so it never touches a single place. The only one we can choose is 37. Here there's no intersection. If I make it 36, yes, there would be at least one intersection at this one place here, -6. A couple just slightly harder systems of equation stuff here. Let me show this one here. So we have a given system of equations with K being a constant. If it has no solution, what is the value of K? So we see here we can do something like that, and we're trying to see where do these never touch a single time. For this one, I could move this slider around, but it's kind of inefficient because I can just go ahead and plug these stuff in. So I can just say here equals -6. Okay, they do intersect there. Equals -2. Yes, again there. Equals 2. Okay, no intersection. Yeah, should be good. And then if I was to make it 6, yeah, there would be. So 2 would be the answer. This one here, it says they intersect at exactly 1 point again. So let me go ahead and try those. Okay, so we have something like this. Now I do have to move the slider around. There's no good option. So -1, is there only one solution at -1? Yep, looks like it because there's only one dot here. So therefore, the answer for this would be -1. So I'm going to be honest with you for a second. If you really think about it, this is kind of like very, very restrictive because we're saying here that these functions can only equal this skinny little line, basically. Only the things in this line would be included within the function. And the reason why that's the case is because we're using this equal sign here. For all the different examples I showed over here, y equals something, this equals something, that equals something, when you say equals, that means it literally is just that exact thing. For this function here, we're saying something is equal to something else, that's why it comes out as a straight exact line. Only one line, no confusion, no ambiguity, nothing. But what if instead of saying equal to it, we said something like it was greater than it? So we said everything greater than this one line. Then obviously we get a lot more stuff. Instead of just saying this one line, we say this line plus everything above it for all of eternity. Likewise, if we were to do the exact same thing with the red line, it would be everything greater than the red line as well. Let me show you what this looks like in Desmos. So like, let's say you have these two lines, this system of equations here, and they intersect at this one place, everything is good. If I was to replace this equal sign for a greater than, now it is everything greater than this line. If I was to replace this one with a less than, now it's everything less than this line. And you may be kind of confused why these are broken. When they're broken, that means that the line itself is not included. And this will make sense because I'm saying everything greater than. I'm not saying everything greater than and equal to, I'm just saying greater than. In order to make the line included as well, we just have to put an equal sign after it, which makes it have a thing like this, a thing under it. So therefore it is a solid line now, and so it would be included in the full thing. Same thing for this one, it would also be a solid line now. And now if you're wondering what the solution would be, it's obviously not just going to be one thing anymore. Now it's going to be all of this stuff that's in both of these shaded regions, because there's now not only one place where they're the exact same thing, there's a ton of different places where they're the exact same thing. Everything in this double shaded region that's both green and blue would be in the new solution set. So it's not like there's going to be one solution. Instead, it might be the case that you're trying to see if one specific point falls within the solution. So I could say here 2, 3. No, that's not in the solution at all. The solution's up here. This is all the way down there. If I was to say, though, 210, okay, it's a lot closer now, a lot closer to the solution. If I was to say 220, now it is literally, barely in. Like I choose the one place where it almost got out. But yeah, this would be included because this would be within this thing and it's on the solid line. If I was to say something here like 320, this also would be in the solution set because it's clearly within the shaded region. If I was to go more than that, though, if I said 340, now if we go all the way out here, we can see, yeah, it's barely outside. It's within the blue, but not both of them. Okay, so pretty simple there. So let me just go ahead and solve some of these. So if we have this one here, let me go ahead and write the two things. Okay, yeah, we got them here. So which is the solution to the given, system of inequalities? I'll just go ahead and try each of these and see which one works out. So 6, 2. No, because we're trying to find places both, in this triangle over here on the left. That's not within it. So A would not be it. 3, 3. Okay, yeah, this would be in it. It would be in both the red region and also the black region, so B would be right. If I want to go ahead and check the rest, we could see here, okay, not it again, and then, yeah, not it again. So these also would not be it. This one, let me just go ahead and write this again. So this might look really confusing, and it kind of is, but let's just look, see what are all the different places where they all have the exact same solution set. So it would be greater than this red thing because it's everything above that. It would be everything less than green because everything below that, everything below purple, everything below that, and then everything here in the black. So it's basically this entire triangle in the middle, just with this one piece cut off over here. So this triangle here. So it's saying here, what is the maximum possible value for y for a point in the solution region? So the biggest thing for y, the biggest vertical thing, would be 10. That is the biggest thing. If we go any higher than that, it's no longer within the thing. If we go any lower than that, well, it would be included, but just would not be the highest possible. So the biggest thing here would be 10. Okay, same thing here. So yeah, we see this whole thing here. So everything greater than black, everything less than green, and everything greater than purple. So kind of like this triangle now over here. Not this one, but just this one because this one includes the black. So it says, what is the maximum possible value for x for this? So if we see here, the maximum would be, 14 here. So 14 is the answer. So one minute thing is that we've said here y is equal to different stuff, like y equals 3x plus 7. Another way you can write this is just say f of x. So just keep in mind, this is literally saying the exact same thing. I know it looks like it's some really complicated, really weird thing. Not at all. It is literally the exact same thing as saying y, just another way of saying it. And so if you see something like this, the one benefit of doing this, well, there's a few benefits, but one of the big benefits is that you can say here f of 3. What this does is it's just going to put in 3 for this thing and see what you get. So it saves some extra time. You're not going to have to rewrite this entire thing. You can just type f of 3. Another thing is you can actually write different kinds of functions based off this. I could say f of x plus 3, and you're going to see that's going to give us a new function on the graph that's different than the one we had before, because now we're just putting x here, and every time we put x, we just add 3 to it. Let me show you what that looks like. So we have this here. This is f of x equals 3x plus 7. If I did f of 3, we just get a value here, 16. So bunch of time, that is what 3 times 3 plus 7 would be, so perfect stuff there. And then we could also just go ahead and say f of x plus 3. We can see here now we have this new red line. It is shifted because now they're taking every single value of x and they're adding 3 to it before they throw it in. So it's almost like they're trying to do f of 1, but then they do f of 1 and then they replace it with f of 4. And so you can see for every single value, they're replacing it with the 3 plus version of that. So that's why I get a different thing here. We could also say minus 3, or we could say something here like minus f. Like there's a bunch of different ways we can do it. There's so many different ways we can modify, change this thing around. You don't have to memorize all that for the SAT because you can just literally put it into Desmos and see what happens when you do the thing. We could also say something here like another function. We could say g of x is equal to this. All this is saying is that we have just another y value, so just a separate one from the original, and this equals this new thing. So we're defining this new function in terms of the original. Hopefully that does still make sense. Some practice problems. Let me go ahead and put the stuff in for this one. That would be the f of x, and that would be the g of x. It says, what is the value of g of 1? So I can just go ahead and say here g of 1, and that gives us 17. This one, same stuff. F of x would be this, and then g of x would be this. Then it says here the graph of y equals g of x. That just is another way of saying g of x. Intersects the axis at points p0 and q0. What is the value of p plus q? So we're just seeing here, when y is equal to 0, what is the x equal to? So for this one, y is equal to 0, and this one, y is equal to 0. -7 and -3. So we just say -7 plus -3, and that gives us -10. One more here. So yeah, same stuff here. We just have these two different things. One is in terms of the other one. It says here, the graph of y equals gx has a minimum at this point a, b. What is a plus b? So the minimum is just another way of saying this bottom thing, this vertex essentially of it. So 4, -1. So we do 4 plus -1, that gives us 3. Okay guys, so regression here. So I know this is something that's known for being more complicated in SAT Desmos. Truth is, I really don't think this is nearly as complicated as most people think that it is. There are definitely more complicated things that can go along with this, but the core act of doing regression is actually not really that hard. What regression is just a Desmos technique. Okay, you probably could have guessed that, but it's not some kind of weird thing. It's not some kind of new term you have to memorize or something. It's just another thing you can do within Desmos. And the reason why you use regression is whenever you have more unknowns than you have equations. Let me show you what this means. For all the examples we've shown before, it's been something like y equals 3x plus 7, let's say, and then y equals 4x plus 5. Count how many different unknown things, aka how many different letters there are here. There's 1, 2, and then the same ones here again. So 2 different letters. And how many equations would there be? There is also 1, 2, because there are 2 different equal signs. So 2 different equations and 2 different letters. That is why this works. In math, you don't need to know the basic fundamental reason behind this because it would get too complicated. But whenever you have a certain amount of unknowns, that is also the amount of equations you can extrapolate from those unknowns. That's just how math works. What if, for example, you had something here like another unknown? So let's say we had z here as well. Now we have 3 different unknowns in only 2 equations. So really bad stuff here. You cannot solve this through regular math means. In order to solve this, you would need another piece of information to make up for the fact that you don't have this thing here. And so if you're given this in a problem, like you have z here and x and y, you would have to be told something else about these 2 things. You would have to be told like maybe x must be, I don't know, greater than 1, or something like x is equal to all real numbers, or z is less than 7. You'd have to be given pieces of information like that because there's not enough information here on its own. You can think of it kind of like a detective. When you have this, it's like you have too many different suspects and not enough evidence to convict any of them. But when it's like you have 2 and 2, now it's like you have the perfect amount of evidence to convict each suspect. So when you're in this situation, when you have more of this and that, and you do have another piece of information, you can use this thing known as regression to figure out what the answer would be. There are 2 key things you must understand when doing this. The first is that anytime you have an x or y, they become x1 and then also y1. So the reason why this is the case is because, like I said, x and y are both variables. They equal to all real numbers. But when you're doing regression, they must become constants. Rather than variables, they now must be just one single number. And so by making it x1, that's just another way of turning this x into a constant. So now it's only equal to one thing. Likewise, instead of having any equal sign, you must use a tilde. So tilde is located at the top left-hand corner of most keyboards that you may use, and it just looks like this on the screen. You usually have to do Shift plus the button to press it, but if you do that, it works. So if I'm writing an equation like 3x plus y is equal to 7, instead of this, I would have to say x1, y1, and then also tilde for that. Now we have regression parameters. We're getting put into the regression thing. If you do not do these 2 things, it is never going to work with the stuff I'm about to show you. So keep that in mind. If you're trying this stuff out on your own and it's just not working, check if you are actually doing this. There's a good chance you are not, because many students, they miss the first time they try doing it. Okay, then how would I put in the other pieces of information I have? Well, all I do if it's something greater than or less than is I do this squiggly thing and just say whatever it is. So if x1 must be greater than 1, I can say x1 greater than 1. If, I guess y must be less than something, I'd say y1 must be less than 8. So now it gives us values that make this thing work. Likewise, it might say something here like x must be all real numbers. So, I'm not going to write all that just because it would take too long, but all real numbers. If it says that exact thing, what you have to do is take that exact thing. So if it's x, you say x1, say equal to, and make a list with these square brackets and do 1 dot 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 10. The reason why this works is because now, rather than having x just be one number, you're literally making it every single number. You're basically turning this back into a variable by doing this. Now, rather than x just being equal to one thing, it's now 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. It is plugging in all those different values for x, so it's kind of simulating as if it were a variable. So if you say something is all real numbers, you must do that as well. And when you solve a problem like this, obviously you just go with the choices that are given here. Now, I know this is probably kind of confusing without really an example being given, so let me go ahead and do that. Okay, so we have this problem. First, let me check if I need to use regression. So we see here we have 1, and then 2, 3, 4 different unknowns, and then only one equation. So there's definitely way more unknowns, so we definitely must use regression for this thing. So let me go ahead and start by writing it in. Okay, so we're given that. Keep in mind, I should not click the slider thing. The sliders do not work with regression problems. The whole point of this is like you're making your own sliders by solving this, so I should not press that. Then I do tilde instead of that, and then the ones after all the x's. We get here all this different stuff, and it also says here for all real values of x. So I have to say here x1 equals 1 dot 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 10. So one more thing. I know this may look kind of confusing, maybe kind of confused, but it's really all you have to do. It's not as confusing, complicated, difficult as it may look if this is the first time you're seeing this. It says a plus b plus c. I can just go ahead and write that in there. It's now saving the a, b, and c in the system, so I can say a plus b plus c, negative 35. Okay, so not that bad. It's not the worst thing ever, as you may have thought it was. Now let's try this one. We have 1, 2, 3, 3 different unknowns and only one equation. So let me go ahead and write this again. Okay, so we have that in there. Let me put the ones after each thing and the tilde as well. So we get this stuff now. It says give is true for all x when x does not equal 3 divided by 5. So this is slightly more confusing, but pretty much it's the exact same thing. 3 divided by 5 is 0.6. So I just have to make sure that is not included in the thing I make x equal to. So I can say x1 equals, well, I mean, that was 0.6. So I can just say the exact same thing, 1 dot dot 10. Because 0.6 is not included within this. If I were to say 0.6, then it breaks the system and now you have an error. So, that's what's going to happen if you don't do that. So yeah, 1 dot dot 10, and now we get p and q is equal to things. And so we can just say p plus q, negative 1. In case you have not been doing so already, pause the video and try out this problem before you see how I do it, just to make sure that you're really good on this. So yeah, I just went ahead and already made it into regression form. So we have this whole thing here, get some numbers. It says for all real values of x. So I can just say here again, x1 equals 1 dot dot 10. We get all that there. T is equal to that, w is equal to that. The value of w here would be 12. Again, pause the video, try out this problem, let me know what you get. Okay, so this is what I'm getting here when I put it into regression form. Again, all real values of x. That's a very common thing for these problems, so don't be surprised if you keep seeing it again and again. So 1 dot dot 10, we get 2, and n is equal to 2 as well. M plus n, so we just do m plus n would be equal to 4. This one here, a and b are constants. If the equation has infinitely many solutions, what is the value of a plus b? You may be kind of shocked by this infinitely many solutions thing, and you may be thinking back to what we were seeing before. But here's the thing. What this just means is that x again is all real numbers. That's all that's saying. So x again must be equal to 1 dot dot 10. And actually, in addition to that, keep in mind, this is literally what all of these problems basically have been saying. When this says it's all real values of x, it's basically saying there are infinitely many solutions. Same thing for this one, same thing for this one. So it's like, this is just another way of saying what we've already been doing. So yeah, we get here a equals 6, b equals negative 9. So we can just do a plus b. And that gives us negative 3. So good stuff there. Okay, the reason why I grinded out so many different regression problems that all kind of look the exact same is because I wanted you to really get familiar with this exact way of doing these problems. Because there's one small twist I'm gonna have to give you for the next few problems we do. Because you may notice all the ones we've been doing so far only had one equation, one equation, one equation, one equation, one equation, so all only just one equation. If you have 2 equations or more, you have to do something slightly different. And students get confused on this every single time I show it to them. So don't be shocked. Don't be, afraid or worried if you get confused on this the first time. Basically, if there are two different equations, so if like you have one up here, this equals that, and then this equals that, what you must do is you must do a bracket system. So you remember the brackets from the list that we were talking about before. You must make a bracket system where basically the left sides of each equation, so let's say L for left, are equal to the right sides of both equations, so right and right. Keep in mind, this is counterintuitive. This is confusing. This does not make sense to our logical brains, because typically what you would see is you would see the left and the right side both connected to each other. You would see them both in the same thing. You would expect it to be like left and then right, and then left and then right. But that is not how it works, because I guess the makers of Desmos just kind of want to destroy us. There's not really any logical or like foundational reason for this. It just kind of is how regression works. So yeah, just keep that in mind. But yeah, left is equal to right in this kind of configuration. Okay, so let's say we have this here. So we have these two equations, and then y must be greater than 1. What I would have to do is I'd have to make this bracket thing. And let me put the left side of the first one in here. So I'd say 3x1 plus 2, because we put the 1s there again. And then the left side of the second one, so 2y1 plus x1. And then end the bracket equal to, aka tilde, the two things on the right side. So that would just be y and then z. So y1 and then z. Again, this should not make sense. If it does make sense to you, then you probably don't know what I'm actually doing, because this should not make sense. This is not logical for how this would, make sense to our minds to work. But we're doing the left sides of both and then the right sides of both. I'm just stressing this so much because so many people get confused on this the first time. I have to re-explain this so many times. I want to avoid the re-explanations here. Okay, then we have to put in this one constraint. We haven't had a problem with constraints yet, but this is fine. So we just do these squiggly brackets for the constraint, y1 and then greater than 1. So that's how we would put that there. We see here this thing, x1 equals that, y1 equals that, z equals that. Keep in mind, regression only gives you one thing, like we only see one value for this. There may theoretically be more values that can make this thing work, but probably for this problem, if that was the case, they would give us more information for the constraints, so that's fine. All I'm really trying to show you here is what is actually going on, the left sides and the right sides. And so all the problems I'm about to show you are going to just use this exact thing, nothing else to it, just that exact rule. So we have this here, the mass of object A is 400% the mass of B, A is 0.02% the mass of C, C is K% of B. What is K divided by 10,000? Let me start by showing you what the different equations actually are. So we're basically saying here A is equal to 400%, let's say, of B. Then saying A is now 0.02% of C. And then C is K% of B. Okay, so pretty good stuff here. And just to make sure I need to use regression, let me check again how many different unknowns we have. 1, 2, 3, 4. So you have 4 different unknowns. And then we have how many different equations? 3. So we have 3 there. Okay, there is a mismatch, more unknowns than we have variables, so we would have used regression. But one thing I'll just go ahead and throw in here, anytime you see at least 3 different unknowns, like, A, B, and C at least, I would just say to use regression immediately, because the way of solving it with a system of equations is going to be way more complicated, even though it may not seem like it right now. If there's at least 3 different unknowns, this is probably going to be the fastest and easiest way to solve it. So just go ahead and get into a habit of doing that anytime you see at least 3 unknown values in the thing. So let me go ahead and put this in regression form. So you have A, and C, and then tilde, the right sides. We can just actually say here 400% of B. Yes, Desmos is amazing. You can literally just say that. You don't have to worry about anything with percentages rules. So that of C and then K% of B. This is what we get. And there's no other constraints here, so it's probably just assumed that this should work no matter what the things are. So it should be fine here. Typically, there could be more constraints, but for this one, I guess we don't need to for what they were trying to find. This is what's the value of K divided by 10,000? K divided by 10,000 would be 200. So therefore, the answer must be 200. This one here, so we have, again, 2 different equations. So let me go ahead and do the left sides. Keep in mind, for this 2x minus 1, we have to put in parentheses. Otherwise, it's not going to make it work. So just keep that in mind. Okay, hopefully you're getting used to this whole regression thing with the left sides and the right sides. Kind of confusing. Yes, I know, but it's fine. So A must be greater than 1 and B must be greater than 1. So I can put those in here as well. A greater than 1, B greater than 1. Good stuff there. What is the value of X? Keep in mind, this is one of the rare cases where it's not saying X is all real numbers. If it did say that, we might have to do something different here, but it is not saying that. So we don't have to worry about that. So it says here X is equal to this thing here. And then it just gives us different values for these. 1.625, as I said earlier on in this video, if I go ahead and click this, it just turns that into a fraction immediately. So no need to worry about anything else. We can see it must be B for this one. Okay, so this one here, we have basically this equation and then also this equation. However, let me just stop you right here. There is one more unfortunate rule that you must know about this. If you're doing this thing here with the brackets, so like I've been showing in all these problems with more than one equation, you actually cannot do this thing with all real values of x. You can't do the thing x1 equals 1.10. Because if you think about what's really going on here, you have a list up here when you say this list is equal to that list. What you would basically be doing here is putting a list inside a list. So like you can imagine how Desmos would get really, really confused very, very fast on that. So you cannot do that. So if you see two different equations, but you also have all real values, you have to just pretend like it's only one equation, and let me show you how to get around this. So I'll just go ahead and pretend like there's only one equation shown here and put this in regression form. Okay, so that is pretty good. And then it says all real values of x, let me put that in there as well. And then it says m plus n must equal 7. As we see right now, 10 plus 1 does not equal 7, so it does not work automatically. We have to put that in there. So what you theoretically could do is just say m plus n equals 7. The issue with this is Desmos wants you to define these different constants in terms of just one constant. It doesn't want you to say m plus n equals 7. They would want you to say something like m just equals, it could say equals 7 minus n. Like it could be something like that. They just want you to have one variable alone on each side. So the one thing I have to do for this is I have to say m plus n equals 7. And if you're familiar with basic algebra, that's not in the scope of this video, but basic algebra, according to those rules, I can just go ahead and say m equals 7 minus n, because we're subtracting n from both sides. So now I can just say here, m equals 7 minus n. And now it works. This basically works as another equation, just kind of like a workaround, where I don't have to write a whole new thing with the brackets, but just works. So this thing will work as well. We see here n equals 2, k equals 7. It says, what are the two possible values for k? The only one that has 7 here would be b, so b is the right answer. Just so I can convince you that this is absolutely cooked, if I was to put brackets around this thing with the x1, you can see here, yeah, they give you this error that cannot store a list of numbers in a list like I exactly told you. No list inside a list, that just too many lists all at once. So that's why we have to use this extra thing there. Let's do this one now. So we have two different equations and it does not say anything about all real numbers, so we can go back to the brackets. Okay, so pretty good stuff here. We have all of this. It says that k must be greater than 0. You can see here k is already greater than 0, but if it was not, I could just go here and say k must be greater than 0. Finally says here, what is u plus v squared in terms of k? So I can just say here u plus v squared, and let me just see what value that gives me, and then I can just go ahead and try each of these myself and see which one matches up with it. So I could just say here 2k minus 7, that's this negative number, so yeah, that's not it. 3k minus 14, negative 6, so that's also not it. 4k minus 7, yep, not it again. We're trying to find this 0.000 number. And then we know it must be D at this point. 6k minus 14, yep, this is the exact same number as up here, so therefore D is the right answer. One more thing here. So another way these kinds of regression things can show up is if you see a function and they say something like h of 0 plus h of this must equal that, and h of that plus that must equal that. You'll remember these functions from earlier on in this video. And when you see something like this, you can also go ahead and just use regression on it. So if it's the exact format with some function of something equals something else, and then you're adding stuff together, all that stuff, what you have to do is you have to start by just writing out the function they give you. So they give this whole explanation here. All this really doing here is just describing this function. So I'll just go ahead and write that there. H of x must equal ax squared, as yeah, it says, plus bx plus c. Okay. And keep in mind, in this situation, you cannot click these sliders. Like, I know I'm making this sound really bad, but like, actually, if you click these, it's going to break the entire thing. So yeah, so then what you must do is do regression without a table with the brackets with this stuff. So I can literally say here, the left sides of this would be h of 0 plus the h of 6. And then the other left sides would be h of 1 plus h of 5. And then we can say that is equal to both 34 and 22. Now we get everything. Like, it just gives us all stuff immediately, and we can just say here h of 3, yep, that'd be 6.2. So 6.2 must be the answer for this problem. So what could have been a very complicated, very confusing problem is actually low-key kind of simple. Now, before we go on to the other type of regression that you'll see on the test, I mentioned earlier in this video that there is one quick thing I want to show you on single variable equations again. So I know that seems probably like forever ago, but yeah, for stuff like x minus 3 equals 6, you can solve it the way I showed you in that part of the video. X minus 3 equals 6. We can just see where it intersects the x-axis, and that would be the answer, 9. But if you want to save a couple extra seconds, and honestly this really does save so much time because it's so easy to do, you can just replace the equal sign with a tilde and put the x as an x1 instead and just use regression on it. And it gives you the same exact answer, and now you don't even have to look at the graph. So it just saves a bunch of time. I know it seems like a small thing. You may think like, okay, that's gonna save like, 2 seconds at most, bro. But if you add that up over the course of a test, you'll notice it just starts becoming so much easier and so much faster to do this than looking at the graph every time. And I would really, really strongly recommend switching over your method to this. I only explained it like I did earlier in this video because I want you to understand the basics of the method. Now that you understand this regression stuff, you can go ahead and switch over to this. And so yeah, just to prove that this works so easily, I can choose whatever thing I want. I can say x1 minus 7 equals 9. Like, yeah, we get a number for that. I can even make a different number if I want. I can say p minus 7. And so we just see what it gets for p. I can say n minus 7. So no matter what, this kind of just makes it so much unbelievably easier. The one thing you have to be careful with on this though is that it will only give you one value. So if you see a problem where it says like multiple solutions or like infinite solutions, or if it's definitely said no solutions, you cannot use this method because it's always going to give you just one exact solution. But yeah, just something to keep in mind on those single variable stuff we talked about before. Now, if you're somebody who's been watching this video very carefully, you may notice something that I said earlier in this video that maybe doesn't make as much sense now, which is what to do with a problem like this. You can see here, we have 1, 2, basically 3, 4, really 4 different unknown values here, but also only 2 equations. So it would make sense that you would actually use regression to solve a problem like this. But here's how I really want you to look at it. You should just go for whatever thing is the easiest and fastest way to solve the problem. So yes, this problem could also be solved with regression theoretically, but the issue with it is that it has infinitely many solutions, meaning you'd have to do the x1 equals the 1.10 thing. But in addition to that, there are 2 different equations. And so remember what we just went over, if you have 2 different equations and you have to also make it x1 ... it kind of breaks the whole system, and then you have to like write the other one as a separate thing. You can't make it in the regression. So all these problems. So in this situation, I would say that doing it with just these systems of equations would be the faster way to go ahead and solve it. You theoretically maybe could use Desmos regression, but it's just faster to use it like this because you're saying infinitely many, and that breaks it if you use the list thing. Likewise, it's worth mentioning that for a problem like this, if it says it has no real solutions, you literally cannot use regression. When you use this tilde sign in regression, that is the same thing as an equal sign. It makes it so the things are equal to one another. If there are no real solutions, you can't say anything is equal to. So the only way you can really solve a problem like this is with these systems of equations again. So really, to explain this in simple terms, I would always say go for regression if there are more unknowns than there are equations. But if it's infinitely many with 2 equations, that's just going to make it much harder. So I'd recommend systems of equations instead. And if it's no solutions, you literally cannot use regression. So I would just not even trying it then. Now, what I just showed you is what I refer to as regression without a table. And by the fact that I say without, you can probably assume, yeah, there's going to be one with a table as well. You know to use regression without a table if you see something like this where there are more unknowns than equations, like I said before. The way you know to use the other form of regression is if you see anything involving a point. Not a point like, a point on a pen, but a point like in math, like 0, 1. That would be a point. Or a point like 2, 3. You understand this because this is just how math works. This is something that can show on the graph like this or like this. And so when you see points in math, you can think of it kind of like a connect the dots. If you've ever played connect the dots as a kid, you would have this book where you have all these different things, you have all these different dots, and you have to like connect it like this. They say which one to do in which order, and it's like a big thing. It makes like a fun, thing at the end of all this different stuff. We are bringing connect the dots back into math because that is what this is really saying. If you have 2 points that are both on the graph, you could theoretically find some kind of function that passes through those exact points. So it could be the case that you have a straight line that just goes exactly through both of these, and this line connects the dots perfectly. That could be what happens. You could also have a curved line that does the same thing. It could be a line that looks a little bit something like this that passes through those exact points. It could be a line that looks a little something like this, okay, that's bad. That looks something like this. So a bunch of different lines. The big thing you're trying to see is, does that line go through those exact points, and does it work? What regression with a table is just a way of finding what line goes through those specific points. Let me show you exactly how to make this work. The first step whenever you see points in a problem is you type the word table, as I showed you a little bit in the intro of this video, and you type in those exact points. Okay, I know not really the most surprising thing there. Yes, obviously that's what you have to do. Then you have basically 2 different options. You can click this here, and they give you different options for what function that you could be choosing that goes through those points. So this is the easiest way by far. I can just say, okay, if it's a linear function, aka if it's a straight line, then I can just click linear regression, and that gives me a straight line that passes through the points. If it's a quadratic, aka a U-shaped or an N-shaped line, I can click quadratic, and we see a quadratic that goes through those exact points. If it's an exponential, I can do that. If it's a cubic, I can do that. And keep in mind, you're probably going to be told what the function actually is. So you don't need to memorize all these different names. You don't need to memorize like linear, quadratic, cubic, quartic. Way too much here if you're trying to memorize everything. I would say that, if you do enough SAT math, though, you definitely are just going to recognize linear, quadratic, and exponential because you're going to see so many different problems using these. So just, you're going to memorize it regardless. Don't really worry about it. So this perfectly works. And you might have to answer a question like, where does it, intersect at the x-axis? Like, what is the x-intercept for this? What is the y-intercept for this? That may be the kind of question they ask you. If you, for some reason, cannot do this thing, like if they give you a very niche equation, like if they say something like y must be equal to x divided by x plus 3 or something like that, you can just go ahead and write the equation manually underneath it. So this is just another way of doing it. You don't have to do both. You should not do both because, there's not really any reason to. You'd just be wasting your time. So I can just say here for this one, y1 tilde. So we use the exact same regression stuff as before. x1 divided by x1 plus 3. And we see here it doesn't exactly match up. There's not an exact place where this goes through those 2 points. That makes sense because it shows like literally a random equation for this, but theoretically what should happen is it should go exactly through those points by writing in this, your manual thing. One thing you can remember is this r squared thing at the bottom is a very useful indicator for whether it actually passes through the points. If it is not equal to 0 or 1, that's an indication it does not go through those points. So always remember that. If it, see here, it's negative 2.88, which makes sense because it does not go through the points. So I'm going to grind these problems a lot until you definitely understand them. So strap in, we're going to get through a lot of really good problems here. And yeah, this one, we have a table and it's being shown here. And so yeah, we just know immediately go and write table here. We put 3, 11, and then 6, and then 23, and then 9, and then 35. So it says here this is a linear function. So I can just go click here and do linear. Yeah, perfect. And it says, what is the value of y when x is equal to 20? So I see this equation here. I can click this thing to just get the equation, and I can just put in x instead of that, say 20. So perfect. Now we have 79 as the y value. So the answer to this problem must be 79. Pause the video, try this out for your own, see what you get. Okay, we've got another table here. Let me put that stuff in. It says this is a quadratic. So I click here and do quadratic this time. And it says, what is the value of y when x equals 6? So this equation, let me just put a 6 in for those. Get here 45. 45 is the answer. This, just the exact same thing. Again, pause the video, try it out. It says it's an exponential function. So I can click here, go for exponential. And it says a and b are constants. What is a plus b? They give us this format here with this being a and this being b. So we know it's 24 and 1.5. So I do 24 plus 1.5. That, of course, is 25.5. This one here, we have another table. Let me put those in. It says it is defined by f of x equals this. And that is not one of the ones listed here. So we don't have any option that really gives us that. So we unfortunately cannot go for this. Instead, I must just write it by hand. For f of x, as I said earlier in this video, that's just another way of saying y1. So I can just say here y1 tilde, again, a divided by x1 minus b. We see here, yes, it passes through those exact points. It connects the dots perfectly. And so it's saying, what is the value of a plus b? Same thing as before, we can just say a plus b, and that gives us 9. This one here, people might get confused on this the first time they see it, but all that they're saying here is they're doing the exact same thing by giving us points, but now they just have a unknown value within those points. So I can do the exact same thing. I can just say table, -2s, and then say 6 here, and then s plus 12. And then we just have this s here, and I just have to choose a random value for s. So remember, I said earlier in this video, whenever there's an unknown within the choices, you can just choose whatever value you want, and it's still going to be the same answer regardless. So that's what I'm going to do here. What I'm going to try doing is I'm going to try out each of these choices when s is equal to 6 and see which one actually gives me something that matches with this thing. I tried out this first one here. For whatever reason, it does not actually give us a thing on the graph for this, but we can just go based off of the value here. RMSE is just another way of saying the R, for our purposes at least. So 26.83, that's definitely not 0 or 1, so we know it can't be A. Same thing for B, we just get this 12.81 number, so that can't be it. But yeah, for C, we do get RMSE equal to 0, so that's probably going to be right. But let me just go ahead and check D real quick. Yeah, D is like 12. So yeah, definitely not D. So don't get worried, don't get confused. It's literally the exact same thing. You just put in these unknowns and just choose a random value. Pause the video and try out this one and see what you get. I did the same thing and I chose 5 for the value. Again, it doesn't really matter where you choose it, just whatever you want. A does not work, RMSE is 13. B does not work either. C does not work, so we know it's probably going to be D. And yep, D does work, RMSE is 0. And by the way, while it's completely fine to just do it the way I just showed you with the RMSE, you can also go ahead and write the new thing up below here and just see if it passes through. That also completely works, and you can see, yeah, it does pass through perfectly for this one. This one here, we have a polynomial that's equal to this, and it says the zeros are -5, 2, and 6. When it says those are the zeros, what it's really saying here is -5, 0, and then 2, 0, and 6, 0 are all within this function. So I can just go ahead and write those in a table. It says here this function x cubed plus that. In case you did not know, that's just what is known as a cubic function. So I can just go ahead and put that. But as you'll see here, it is messing up. This sometimes happens when you use regression. Sometimes it just kind of gives up. And I honestly kind of get frustrated with Desmos when it does this, because obviously that's not what I'm trying to go for. I'm not just trying to find a straight line. Obviously I didn't do all this work just for all the values to be 0. That's obviously not what I was trying to do. When that does happen though, you can typically get around it by just writing it out manually like this. So when I write it out manually, we see here, this is what we get for each of the things. And so yeah, this is actually what the function is supposed to look like. And it does pass through all the points we were given. A plus B plus C, we just do like this, and that gives us 29. So 29 is the answer here. Okay, most of these have been pretty simple so far. Let me go through a couple that are a bit more complicated though. We have this one where the graph of quadratic, we have these 2 points. Okay, so that part's pretty simple. Let me just go through that first. And then at quadratic, we go through like this. But let me see if you can tell what the issue is with this. They say that it has the minimum at 3, -8. If we do 3, -8, that is this dot here. The minimum would be referring to this bottom part right here at the tip of the quadratic. So therefore, the minimum is not 3, -8. So therefore, what we were just given here was a complete scam. It is not what we're trying to find for this thing. If we were to go for this as the answer, we would not be choosing the right one. In order to basically force the minimum value to be a certain thing, we have to do this thing called the vertex form equation. If I took this exact equation, y equals a times x minus h squared plus k, hk here is referring to the vertex, aka the minimum or the maximum of the quadratic. So therefore, we can use this to force the value to be where we want it to be. We can say y1 equals a, x1 minus, instead of h, we can say here, it must be 3, -8, so we can say minus 3 squared, and then plus the k value, which would just be -8. Now we've basically forced it to do our bidding, so to speak. So we have 3, -8 as the bottom thing for this quadratic. Okay, so now it works, and it says, what is the y-intercept of the graph? The y-intercept is just where it intercepts the y-axis, which is the vertical axis, if you haven't been able to tell that so far. So vertical axis, it intersects it right here at 10, so therefore the y-intercept would just be 10. So that's an example of a time where they literally force you to do it manually. Sometimes that happens. Another time they force you to do it manually is if they have a circle here. So they see they have a circle passing through these points. Let me go ahead and do that. The thing with this is we just don't have an option to choose circle as one of the things here. If we did, we could just go for that, but we don't have that option. So we have to also know what the equation for a circle is, which is x minus h squared plus y minus k squared equal to r squared. In case you're wondering, HK again would be the center of the circle. It's the point right in the middle of that circle. And then R is just the radius, aka how big the circle is if you go from the center to the outer point. If we do that there, we get -5 for R, but just keep in mind, -5 squared would be this exact same thing as 5 squared. And so it's just trying to say 5 squared. You can't have negative radius for a circle. That's just not how geometry works. So the radius would actually be 5. Go ahead, pause the video, try to solve this one real quick. Okay, so we get given these different points here already in a graph. Sometimes you can see a problem like this. Let me go ahead and start by putting those in. And it says here, it is written in this form, basically the vertex form exactly. So something like this again, it says, what is a plus h plus k? We could just say a plus h plus k, and that'd be -6. So that's the answer. Pause the video for this again. We have these 3 points now, so let me put those in. It says here this is an exponential function, so I can just go ahead and do this again. Finally, we can go back to using this here at the dropdown. It says, what is f of 4? So I can put that there and do 4 in here for that. We see there that would be 5. So 5 would be the answer. One last one for this regression section. So we have this function, which is just another way of writing a quadratic. This is what a quadratic means, in case you're wondering. It just has the vertex at x equals 8, and then these 2 points here. In case you're wondering, these are just ways of writing points, because what this is showing is the x value, what this is showing is the y value. So keep that in mind. This may not look like points, but those are literally points as well. So since there are points, I can just go ahead and write a table again. I can put in 2, 7, and then 5, 13. And then it says here that it has the vertex at x equals 8. If I do a quadratic normally, we can see here this is not 8. So therefore, I have to do the vertex form thing again. Notice here we are only given that it is the vertex x equals 8. We don't know what the y is for that vertex, so I just put in this for h, and we don't know what the k would be yet. Okay, it says f of 17, so I can just go ahead and put this in there. In order to do that, I can just say here a, and then put 17 in there instead of x, minus 8, square that, and then plus k, and we get here negative 3. So negative 3 would be the answer. I just want to show one quick exception. This is not going to be a very common problem or anything, but you might see this where they have these different, points, but they're in the choices rather than the problem. If the points are in the choices, you don't have to do the whole thing that I showed you here. You can just treat this like a system of equations and just put in a random value for the thing that they're giving you. So I would start by putting in these two. These are two different functions, and we see here they're the exact same thing here. If they're the exact same line. If I remove one, we just see the other one. So important to note, but not going to really be too important for this problem. So we can just go ahead and try each of these different things, choose a random value for r, and see what we get and if it is actually on this function or not. For that first one, it is not on the function. No matter where it is not on this exact line. So A is not it. For the second one, it is not either. B is not the answer. For C, it is also not the right answer. But finally here for D, it would be the right answer. No matter where we put R, it is always on this exact line. Therefore, D is the correct choice here. The points always match up with the line. So the only distinction between this and the other ones is that we have points in the choices rather than the problem itself. When they're in the choices, that is the one exception to when you use regression with a table. Every other situation, I would really strongly recommend to start with the regression with a table as your first choice on how to solve it. Pause the video, go ahead and try this one real quick. We can see this is a lot easier because we just tried the first one, t 12 minus 3t divided by 4, and it is automatically the one that is on the line. If you really want to make sure, you can try B, C, and D, but you'll notice that, yeah, they are not on the line, so they're not the right answer. Real quick, a quick checkpoint. That's everything I'm going to talk about in this video involving regression. Yes, we do have a bunch of different things we still need to talk about in this video, but none of it is going to be as long, as hard, or as confusing as this, so be glad you're not going to get anything as weird as this again in this video. So the next major topic that we have here is known as equivalent expressions. The way to think about this is that I've talked a lot so far about these different functions. And so, for example, I've said stuff like y equals 3x plus 7. This is just, for some reason, a function I love talking about. I use this as examples pretty much every single time for whatever reason. But if you think about it, there could be another way we could write this exact thing that would give us the same exact line on the graph, same exact everything, but just with different numbers for using it. Instead of saying 3x plus 7, we could say something here, like instead of 3, we could say 6 divided by 2x plus 14 divided by 2. Now, if you're familiar with like basic algebra concepts, you would know 6 divided by 2, that's just another way of saying 3. 14 divided by 2, that's another way of saying 7. And so if I go here in Desmos, I can type the first equation, and then I do the other one, and we're going to see it is literally going to be the exact same thing. It's the red on the exact same place that the black would be originally. And so this is what equivalent expressions are. You can have multiple different things that have the same exact meaning in terms of what they show on the graph. They just look slightly different. And there are many different ways this can happen. There are many different ways this can occur, but this is the major way. But keep in mind here, this works in the way I'm showing because we have x and y. If there are not x and y, it would be slightly different, but overall the same kind of logic. You could say something here like, I don't know, let's say q is equal to 1 divided by 3 times s. And so, this is how it works. This is the relationship between Q and S. Another way of saying this, though, is that Q would be equal to 6 multiplied by S. That's just the exact same thing, again, because of these algebraic rules. If you multiply both these by 2 divided by 2, that'd be 2 over 6 for what you get for this instead. And so also you can check this by putting in different values for each of these. We could say that S is equal to, let's just say it's equal to 3. In that case, Q would, of course, be equal to 1. In this case, if S is still equal to 3, Q would still be equal to 1. It's the exact same thing, it's just another way of writing this to start out with. And it doesn't matter what value we choose. If we made, instead of 3, if we chose it to be like, I don't know, 6, it would just work the exact same way. This would be 6, and then the other one would instead be 2. And then this one would also be 6, and this one would instead be 2. So just the exact same thing. It's just another way of writing the stuff. Okay, so this probably seems really simple, and it kind of is actually like pretty simple. So let me go ahead and show some examples very quickly. So we have this one where it has the positive quantities v, p, and r, which gives r in terms of v and p. Remember what I said before, whenever there's something like a constant in a choice, you can just plug in random values for the different things, and you'll always get the same exact answer no matter what values you choose. So I'm just going to go ahead and say p is equal to, I don't know, 3, r is equal to 4, and just see what we get. So you can say v is equal to P times R divided by P plus R. So yeah, that works. We get this 1.714 number. And then I can go ahead and try out each of these and see which one gives me the same value for R. So we're looking for 4, so it must be equal to 4. So VP divided by V minus P, that would be -4, so not quite, pretty close though. For B, it would be VP times P minus V. And yeah, that would be 4. So yeah, B is probably going to be the right answer. But I always say with these, go ahead and just move around these a bit just to make absolute sure that it still ends up being the exact same thing. Because occasionally you can get really, really unlucky and choose the one case where it would be the exact thing that is different from all the other ones. So if you change it at all, it just completely changes the entire thing. So instead, move it around a bit. We can see here though, 8.5, 8.5, yeah, they always end up being the exact same thing. If I tried C and D, we would discover that they don't equal the same thing for R. Okay, so pretty easy there. Let's just try another one, pause the video, give this one a shot, and see what you get. Okay, so I just went ahead and chose some random stuff for K, M, and N. Keep in mind, you should never choose 0 or 1 for any of these because that just messes everything up, because 1 minus 1 is, of course, 0. And if you divide anything by 0, that's typically a bad thing. And so, yeah, don't do that. But with that out of the way, we see here S is equal to this random number, and we're trying to see here which gives M in terms of the other stuff. So I can just plug in each of these and see which one gives me the thing for M, which would be 6. So the first one here, K times S to the squared plus N. Yeah, that would be 9, so that's not it. This one here, it would be S squared divided by K and plus N there. Okay, yeah, that equals 6. So therefore, again, B is going to be the right answer. If I move around this stuff a bit, actually, I'm going to be completely honest with you. I was going to just tell you guys the answer is B, but yeah, I realized when I move it around, we can see the exact thing I was warning you about before. Yeah, if I move this around, now it does not end up being the exact same thing. Now M is equal to 7.5 and this is equal to 5.4. So yeah, B would actually not be the right answer. It only worked for that one random thing we chose. So we have to keep going down and see what other one, we have here. C does not work. Yeah, 7 and -3. But then finally here we get to D. And yes, this looks like it is the one that works. 8.1, 8.1, yeah, 7, 7, whatever you choose. Yeah, it ends up being the exact same thing. So there's exactly what I was trying to tell you in action. I did not even expect that was going to happen, to be honest with you, but yeah, that happened. I just want to quickly mention though, as well, if you see a problem like this, one thing you can do alternatively is you can just use regression to have it choose itself what each of the different things is. So I could just say here S, then tilde, square root of then K divided by M minus N. And yeah, we see here N is equal to 1, but that's probably going to be okay, assuming all the other ones are not 0 or 1. So yeah, then therefore, from that point on, we could just do the exact same thing we did before, divided by squared plus N. We see here 1.84, same thing as here for M, so that would be the right answer. So just a slightly different way you can solve it if you just want to save, I guess, a couple of seconds, but it's not really enough to make it worthwhile to do this all the time. Now we have one with the X's and the Y's, or I guess just X here. And so this one, we can just go ahead and use the graph thing I was showing you before. So 9x squared minus 25, we divide that whole thing by 3x squared plus 11x plus 10. We're trying to see here which one of these equals the exact same thing. So if I try the first one here, 3x minus 5 divided by x plus 2, yeah, that actually works. Yeah, it's the exact same thing just immediately. If I was to try one of the other ones, like if I change this for B instead, yeah, we see now we have this one line here that's not the exact same. But yeah, if it's the same as A, yeah, the exact same thing. So therefore A must be the right answer. Similar thing here, though we do have a constant in there as well. So again, we can just choose whatever number we want for that. We have x squared minus a to the 4th. And then we divide that whole thing by x plus a squared. Again, then we add the slider here. I'm just gonna make it 5 just to keep it good. And then just see which one of these gives us the same exact thing. So x minus a, no, that's not the exact same thing as the green. So that can't be it. A squared. Yep, okay, yeah, that should be it. The exact same line, yeah, every single play is the exact same. Okay, B must be the right answer, therefore, for that. On to factoring here, I'll be honest, this is a little bit of a more complicated thing to explain in simple terms, but here's basically the way it works. If I was to say to you x minus 3 multiplied by x minus 4. We have these two things and you multiply them together, you get something in a graph for that, really great stuff. But if you also think about it, what is going on here is we have two different factors. We have x minus 3 and then x minus 4. Each of these would be factors of the bigger overall thing when you multiply them together. And that's just literally what factoring is. The reason why it's slightly more confusing than that is because it's not going to look this clean every single time. Because think about it, if you're familiar with math, algebra 2 type stuff, foiling, you can go ahead and multiply all this stuff together. You can FOIL it out. And that's going to give you a brand new equation. Specifically, it would be x squared minus 7x plus 12. This would be the thing. So this is the exact same thing as this. So back to the equivalent expression stuff. This is the same thing if I was to to do x minus 3 times x minus 4. So yeah, you can see same line. But yeah, the important thing here is that these will both be factors of it. And the way you can tell whether it is a factor is because if you write it in here, it is going to have the same exact intersection here on the x-intercept as the bigger thing. So you can see here 3, 0, the blue line goes through it and the purple line goes through it at the same exact point. Same thing if I was to do 4, just the other one. And so the reason why this works, I mean, I honestly think the reason is too important for this, but you can just kind of think about it logically. This thing is made up of these values here. You know, that they are literally the building blocks of this bigger overall thing of x squared minus 7x plus 12, even though it doesn't look like it. And so if we do, for example, 4 minus 4, that would of course equal 0. If we do 3 minus 3, that would equal 0. So that's why it says here 4, 0, because we put in 4 and we get 0 out for that thing. It's a function, as we've been talking about this entire video. But it should work the same exact way for the bigger purple one because it is made up of that. It includes this as one of its core building blocks. So if we put 4 in for this purple one, it should be the same exact thing where it ends up being 0 at that exact same place. If it does not end up being the same exact x-intercept, like if we put it x minus 8, we can see here, yeah, they're not factors. You know, pretty simple stuff there. Let me solve a couple quick problems. We have this whole function here, so let me write that in. I'm just gonna choose a random value for k to start out with. It says x minus 5 is a factor of this. So I would put x minus 5 in there as well. And then we can just see where would k have to go to make it where they have the same exact x-intercept. It looks like, yeah, it would be -6. It would have the same thing at 5, 0. So therefore, the answer must be -6. I'm probably going to discover that there seems to be no other place where it would work out where it ends up being the same exact x-intercept where if we move k. For this one, it looks a bit more complicated, but it's pretty much the same stuff. Let me start by writing out both of these. So yeah, I put in these two different functions, and then x minus 4, we get this constant a. And now this looks a bit more messy, I'll be honest here, but it's just the exact same thing. We're trying to see here what value of a would you have to choose to make it where we have the same x-intercept for this purple line as both the blue and the red one. So we kind of have to move it around a bit, but yeah, we can see here, yeah, I think, yeah, if we do a equals 2, we have this big, multi-intersection point 4, 0, where the purple goes through the x-axis, red goes through the x-axis, and the blue also goes through the x-axis. So therefore, the answer should be 2 for this. Yeah, B. Okay, so you can see here, yeah, as I told you, this stuff is a lot simpler than all the regression stuff we were doing before. But yeah, let's just keep on moving on here. So one thing you can do with this, I mentioned to you at the beginning of this video, you have this mean and then median stuff you can just use in Desmos. There's nothing else I need to say with that. But one thing I just do want to throw in here is that you can also write these in terms of equations. So let me just show in Desmos. I could say the mean of, let's say 1, 2, 3, 4, and then let's just say n for a random number. And then I'm going to use regression on this just to make it a bit simpler because this is basically a single variable equation, 7. So now we see what n would have to be to make this work. The mean of 1, 2, 3, 4, and 25 would be 7. That's what it would be. If you think about it, one way you could imagine this is kind of like if you are taking a class at school and you got like bad grades in all the previous tests, like if you currently got like a 50 and then like a 60 and then like a 30 on one, and you're trying to see what grade would you have to get on the last test to get like, I don't know, a 90 in the class, you could see you'd have to get a 220 on the final exam to get a 90. So useful thing to use, I guess, for classes as well, but yeah, you might be cooked if you're in this situation. Kai's scores on the first 3 tests in the course were 82, 91, 88. What score must he earn on the 4th? So it is 90. Okay, so exactly like I showed you in the example before, 82, 91, 88, and then let's say n for that, and then tilde 90. So yeah, he must get exactly a 99 on the last one in order to get that beloved 90 for the class. This one, the mean of the 5 numbers 7, 12, m, 19, and 25 is 16. Let me start by just writing that. So mean of 7, 12, m, 19, 25, that would be equal to 16. So m must be 17. Okay, we got that. And then what is the median of the 5 numbers? I could just say the same thing, median 7, 12, and now we have m saved, so we can say that, 19, 25. So 17. Yeah, it would be the exact same thing as the other one before. Okay, on to SOHCAHTOA now. If you're not familiar with what SOHCAHTOA is, I would highly suggest just watching my full right triangles video, which is also on the YouTube channel you're watching right now. I would not recommend trying to just learn it for the very first time on this video, but just for a brief overview of how Desmos plays into this, I talked before in the intro again about how to use sine, how to use cosine, how to use tangent in Desmos. You can just go ahead and write single variable equations using this in a similar way to what I showed you for the statistics. So for example, we could, if we know that we have an angle of 30, we could say sine of 30 is equal to, let's say the opposite, let's say we don't know what that is yet, and let's say we do know what the hypotenuse is, let's say it's 10. So sine of 30 equals whatever this is equal to over 10. And we can just put that in. So yeah, with this, we can see the opposite would be equal to 5. And yeah, we can do whatever we want with this. We could say if we know the opposite is that and we're just trying to find the hypotenuse, we can say the hypotenuse equals 12. So very simple stuff there. The one thing you must remember though with this is that if you're using degrees, which you probably will be if you're using sine, cosine, tangent, you must go over here and put it into degrees mode before you start. It's going to be on radians mode and you're going to get some kind of weird answer like -6, which does not make sense for hypotenuse. So you must go ahead and switch it over to degrees to make this work. You know, I kind of hate that Desmos doesn't just automatically do this for you because it kind of is just like forcing students to make errors that they wouldn't want to be making. But unfortunately, this is how it is. You must switch it to degrees, otherwise it's going to be cooked. You do not have to like literally switch to degrees when you first start taking the SAT. Like you don't have to make that like part of your routine. But I would definitely say like anytime you see a SOHCAHTOA problem, you definitely, you have to basically. So, for example, how this could show up in a right triangle, one of the acute angles is 32 and the hypotenuse is 20. What is the length of the side opposite to 32 to round to the nearest 10th? Just for a brief overview of how sine, cosine, tangent works, this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse. And so if we see here that it's 32, we could just say here that, if we're trying to find the opposite side, we could say sine of 32, and that must be equal to the opposite divided by 20. It is in degrees mode, as I showed, so therefore the opposite must be 10, and we says to round to the nearest 10th, so 10.6. We could also see something like this, sine of x is equal to cosine of 58, so I could just do sine of x1 equals cosine 58, and that would just be 32. So the answer would just be 32. Literally that simple for this. Okay, the very last thing I have as for a major concept to go over is circles. Really, I've kind of already discussed what you need to know about circles involving Desmos because I said what the circle formula is. X minus h squared plus y minus k squared would just go ahead and be equal to r squared. And hk is just another way of writing the coordinate system for the center of the circle. And the r is just the radius of it. So that's what you have to put in. You get a circle, you put this in, you're going to get a circle out for the thing on the graph. So that is what a circle would look like. And you just kind of have to solve some problems with it. Sometimes you're going to have to figure out what the center of a circle is. Like you might have a circle like this, and you have to use the midpoint formula to figure out the center of it. As I showed you kind of earlier in this video, you might have to figure out what the diameter of it is using the distance formula. So there's a couple like random stuff there, but it's pretty much just regular Desmos stuff for the most part. So this one here, we have this equation for a circle. So plus y squared minus 10x plus 6y is equal to 15. So we get this here for this circle and says, what is the radius of the circle? To do that, I can just figure out what is the distance between the two things and divide it by 2. That is what the radius is, the overall distance of a circle, and divide that by 2. So I can put in this point 5, 4, let's say that's equal to A. And then we have this point 5, negative 10, that's equal to B. And I can say distance A, B, and then divide the whole thing by 2, we get 7. So that is what the radius would be, and this one, we have this circle. It says, what is the value of AB if AB is the center of the circle? So let me write that. Okay, so the midpoint of this, I would just go ahead and do this thing, -4, 9, and then -4, -5. And the midpoint would be -4, 2, according to this formula. And so that would also be the center of the circle. One thing that you may notice is that I'm not typically using the outsides over here for the thing I'm using, like this, -11, 2, or I guess this would be 3, 2. That's just because those can often be confused with the x-intercept and the y-intercept. So I always just recommend going for the topmost point and the bottommost point and use those to figure out what it would be. Don't worry about anything else. Then one more over here. We have this circle, and now we don't have to worry about distance or midpoint. We're just trying to see which lies within the circle. So I can just go ahead and try out each of these. 9, 3, that's outside. -2, 4, that's outside. 7, 4, that's... I guess that's... it's barely outside, I guess. And then we have here finally 0, 4, yes, that would be barely within the circle, so therefore it would be D. Okay, here's probably the most important part of this entire video. When do you actually go ahead and use Desmos on the SAT? Well, let me start by giving you, I guess, the simple answer. Anytime you see something like an equation, anytime you see something like points, and anytime you see something involving calculations, that is a good indication that you should use Desmos. So that's a simple answer, but let me actually explain it in a little bit more of a maybe more strategic way. And that's that you shouldn't really think about Desmos in this way. A lot of students that I talk to, they have this idea in their mind that there are some problems that are definitely Desmos problems, and then there's some problems that are definitely not Desmos problems. And so if there's a Desmos problem, you should always use Desmos. You should never not use Desmos on it. If there's a non-Desmos problem, you should never use Desmos on it. If you ever use Desmos, you're absolutely screwed. But that's not really how I look at it. Instead, I think about it more like this. On the SAT, on every single SAT that's ever been taken throughout all of history, I guess for the last 100 years that the SAT has existed, the top goal for every single student has been to maximize two things: speed and accuracy. And I mean, yeah, this obviously makes sense. If you are very, fast on the SAT, that's great. That's a great thing. You're going to finish your test and have all the questions answered. But it literally does not matter if you have zero accuracy. If you get every single question wrong, but if you finish the test within 10 minutes, that's not going to be a good score. It's going to be a really, really bad score. Likewise, if you're super accurate, you get every single question right, but your speed is terrible, you're taking an hour for each module, that's also going to end up being pretty bad because you might be really good with all the questions you do answer, but you are going to miss many of the questions. So you're trying to maximize both of these things. And if you had literally perfect stats in both speed and accuracy, you'd be just guaranteed to get a 1600 on the SAT every single time. The issue is most people don't have perfect stats in both of those. Even I don't really have perfect stats in both of those. I think speed is really kind of what has messed me up, and a little bit of accuracy. And so as a result of that, the way you should evaluate literally anything on the SAT is, will it maximize both speed and accuracy? Or will it maximize at least one and have some kind of good reason not to maximize the other? And so that's how I view Desmos on the test. It's not whether there are some Desmos problems and some non-Desmos problems. I just solve every single math problem the regular way I would. Do step 1, step 2, step 3, step 4. And if Desmos could be used on that step, I use it. If Desmos is not a good idea, if it doesn't make it faster or more accurate, I do not use it. And I just go throughout the entire list, Desmos or non-Desmos. And this may seem ultra basic, but it's so much better of a way of thinking about this because now you don't have to worry about looking through some complicated flow chart oh my gosh, do I have to use Desmos? Is this the exact problem wording where I have to use Desmos? You can just think, okay, do I know a Desmos technique on this step of the problem? If yes, do it. If no, don't. And you may think about this, this may remind you very heavily of AI. You're probably familiar with the concept of AI slop. Many people are making a lot of, things with AI that do not need or should not be made with AI. And there's kind of this idea that goes around people sometimes, when they first discover AI, for example, where they think if you put AI in something, it must be better. If you have a song, that's fine. But if you have a song made by AI, it must be awesome. If you have food, that's okay. But if you have food that's made with AI somehow, that must be awesome food. If you have a picture not with AI, that's okay. But if you have an AI picture, that's awesome. Now, you guys may not think that. Hopefully you don't think that. But many people, especially older people, I found, typically have that kind of mindset. If there's AI in it, it must be better. But it's really not how you should think about it at all. The way you should think about AI is, will this make whatever I'm doing, either faster, or will it make it better in some way? And that is the only question you need to ask. Will it make it faster and or better? If that's not the case, I should not use AI. If I'm trying to make food, probably AI is not going to make it better. I don't know how AI can make food, probably pretty badly. And I don't know how it could really make it faster either, because if you have a good chef, the chef does not need AI to know food. As I explained in the example at the beginning of this video, even though it's a crazy long time ago, a good chef can just figure out recipes off the top of their head. And so that AI should not be used in food. But if you're trying to write an email, then yes, it would make it probably faster, might even make it better, because you probably could have better wording using AI. So AI would be a good usage in that. Let me show you some examples of this concept in action. So for this problem, we have this whole right triangle configuration here. Let me write out what I think are probably the steps to solve a problem like this. First step would probably be to write out the thing. As I already have done here, you have to write out the triangle, otherwise you have no idea what you're doing. Step 2 is you have to set up an equation, make an equation for the triangle. And then step 3 is you have to actually solve said equation to figure out what the different things would be. So these are 3 different steps. Can Desmos make any of these steps faster or better? For writing it, no, Desmos cannot write a right triangle. So I should not use Desmos for that, absolutely not. And as you can see, I just wrote it on here. I would never use Desmos for a step like that, because how even would you? For an equation, yes, Desmos is really good for that. You can write an equation in Desmos, and that makes it pretty much, easy. So sin of 32 equals, we have the opposite divided by 20. Okay, pretty good. And then solving it, Desmos is really good for that as well. Desmos just did it automatically for me. So Desmos is good for that third step. So Desmosable and then Desmosable. Let's look at this problem. So we have this here, this function that I showed you before, where it is drawn here, and trying to see what is a plus h plus k. The steps for solving this problem, I would say probably are you have to, first of all, figure out a way to write the equation in the vertex form. So start by writing it in the vertex form. Second, it isn't really even anything second. It's pretty much just write in vertex form. I guess if you had to put something, you could say second, add together the things. So pretty easy stuff there. And so let's think about this, writing in vertex form. What if we did not use Desmos for that? I mean, yes, you could do it. Yes, every single problem on the SAT is solvable without Desmos, but it would take a long time. Like, it would take a bunch of algebra that I have to write out. I probably would have to like use the quadratic formula and all this stuff. Well, maybe not that, but like at the very least, I'd have to do a decent amount more work to write this and make it into vertex form. If I use Desmos, it makes it so much faster and honestly so much better as well because I'm less likely to make a mistake. So yeah, definitely that would be Desmosable. So I can do that by doing like I did before, table. We can put in here -1, 0, 5, 0, 2, -9 like I did before. And then yeah, to write the thing, to do the rest of it, I could say a, then x1 minus, yeah, I guess what would it even be? 2 squared plus -9. And yeah, we have the exact thing here, minus h plus, yeah, instead of -9 be k. We have this exact equation for what we'd put in. And then we see here a, h, and k, a plus h plus k, we get -6 for the answer. So yeah, that's the adding step down there as well. So yeah, obviously that's better with Desmos too, because, you know, why add something by hand if you can use Desmos for it? This one here is maybe more of like a gray zone, you could argue, because this one we see here, you know, if I was to write out the steps for this problem, I'd probably say step 1, we have to get the equations in the same format. We try to make it so both these equations say the exact same thing, because if they have infinitely many solutions, that means that they're literally just the exact same equation. And then I would just go ahead and add together again the D and E. Now, putting them in the exact same format, that arguably could be done by hand pretty well. Like, it would involve some algebra, you'd have to manipulate it a bit, but you can do it by hand. However, I would argue that it is definitely faster to put in the same format using Desmos, because I can just go ahead and say 6x plus 9y equals 21. And then dx plus 12y, remember I have to put instead of e, f. And I just do this, I just move these around a bit. It might take a bit of work just to make sure it's in the right thing, but besides that, yeah, I just make this, I think it was like that, and so then bring it up to 28. So to me, that took maybe like 10 seconds of moving it around. That would be much faster for me than having to write this out into algebra and do all this different stuff. It'd be faster, and so therefore, if it's faster, that's one of the two things you're trying to maximize, so therefore I would recommend doing it. For you, it theoretically could maybe be a bit faster to do it by hand. But I'd say for the vast majority of you, probably that's going to be faster than using algebra because we hate using algebra. Like, nobody really loves using algebraic operations. So probably it passes the Desmos test. For adding, of course, yeah, definitely pass the Desmos test because, yeah, D plus F, that's a lot faster than doing it if I had to do it, you know, by hand. And so as you can see here, I'm literally never thinking to myself, is this a Desmos problem? I'm just evaluating every single step individually in the exact way I just showed you there. So yeah, that's great and all, but I know probably for a lot of you, you want like a more specific guide. So you can just say, okay, I need to do Desmos on this type of problem. Again, I would really not recommend relying on this as like an end-all be-all. I think what I just said before is a much better way to go about doing this, and that's how you should evaluate Desmos. But if you want just like a basic overview just to keep yourself on the right track, here's what I would say. Like I said earlier, just like, you know, a couple minutes ago, what you need to do is use Desmos whenever you see anything with equations, whenever you see something with points, and anytime you see something with a calculation. Those are the top 3 times. But more specifically, if there's anything that involves a single variable equation, a system of equations, anything with inequalities, that's when you do Desmos algebra, aka the stuff I did at the beginning of this video before I got into the whole regression thing. If you see anything where there are more unknowns than there are equations, that's when you use regression without a table, as I've already said before. If you see anything with points given, that is when you have to use regression with a table. If you see any of this other stuff that we talked about later on in the video, you can also use Desmos for it, but just, you know, other random stuff, not really any kind of specific thing you're looking out for. And then if there's anything beside that stuff, such as algebraic operations, geometry, and interpreting word problems, that's when you do not use Desmos, you just do it by hand. When I say algebraic operations here, I mean if you say something here like 7 plus x is equal to 8, and you like subtract 7 from both sides, like if you minus 7 here and minus 7 here, you obviously cannot do that kind of thing with Desmos. But for a problem like this, you could just put this into Desmos and solve it that way, so it doesn't really matter anyways. Also with geometry, like I said before in that example, you can't like literally put a shape into Desmos unless it's like a circle, so that would not work. And then also like interpreting word problems, that's just on your own, it's your own ability to interpret what a problem is saying if it's a math word problem. So obviously Desmos is not going to be a thing that really helps you there, of course. Also, if you have questions on literally anything in this video, feel free to drop it in the comment section below. I'm going to try to respond to every single comment on this video, so if something did not make sense, if you want more of an explanation for anything, just let me know and I'll try to get back to you as soon as I can. One more thing before we end this video off, if you're currently below 1400 with your SAT score and you want to get to 1400 plus, check out Mission 1400 plus with the link in the description below. We have helped tons of students improve their SAT scores to the stuff that you're seeing on the screen right here, and we think we could probably help you as well, even in the time before your next test. You get a bunch of resources here, including the full math course, the full reading and writing course, and also one-on-one support from me, which you can't really get anywhere else. I'll see you guys in there. It's completely free to try with a free trial, so there's also no risk at all. Have a great rest of your day. Good luck in the SAT. Hope this video was able to help you, even though it's really long, and make sure to always stay Gucci.